So we will today basically finally use the equation to solve our problem of flow around the sphere. So let me just open a sketchbook and open a new one. All right. So just to recap, what are we doing here? So we are trying to solve flow around the sphere, and for that the problem is that we will not be able to reduce our flow to a single velocity or velocity in just one of the coordinate directions that depends on only one coordinate. As a matter of fact, to go around the sphere, because sphere is curved in at least two orthogonal directions, I actually need two velocities that are not non-zero, and in the spherical coordinate system, there VR and V theta. I need two of them, and they both depend on R and theta. Okay? So if you just plug things into an Navier-Stokes equation, it becomes two coupled and two coupled. We also, of course, have pressure. So with those three things in place, there's no way for us to simplify it enough to actually use analytical tools to solve. However, Stokes did devise the way in 19th century to solve it, and it's called stream function approach. So just to recap what we did so far, basically we started with Navier-Stokes equation. Okay. And just to remind you, it's plus v dot grad v is equal to mu and this is generalized pressure. Okay. So this equation with some rearrangements are basically taking curl of equation and using vector identities to simplify. We actually got equation of change for vorticity. Okay. And basically that equation of change of vorticity is then, so vorticity being curl of V. This equation became, oops, not partial T, partial W. T minus curl of V curl W and minus nu Laplacian of W is equal to 0. So this is equation of change of vorticity. So benefit number one, okay, is which one? What's missing from this equation of vorticity? Pressure. So pressure, there's no pressure in this equation. So if we solve this equation, we would get the velocity field, and then I can plug velocity field into Navier-Stokes equation, and with some boundary conditions, I can figure out what pressure is. You can see gradient of pressure in Stokes equation, so Navier-Stokes equation, so it's not a necessarily difficult thing to solve once you have velocity field. And benefit number two is, okay, if I'm actually solving 2D flows, right? When looking into into 2D or planar flows. Of course, of incompressible Newtonian fluid, then your V is Vx, Vy, 0 as a vector. So you can actually define a stream function such that this is equal to minus, and the function we refer to stream function as psi. This is partial minus partial psi partial y and partial psi partial x. I mean, if you have velocity field already, then basically these two partial differential equations, they're simple enough that you can integrate them and find this stream function. Okay? And the stream function has it has a property that it's constant along the streamlines of the flow. So along every streamline, it's going to be a different constant, but if you're just tracing one particle and its path in the flow, stream function is going to be constant. Okay? We can actually see that for stream function, if it's a stream function that is corresponding to a velocity field of incompressible flow, then you can actually see that automatically divergence of V is equal to 0. Why? Well, I would take partial x of the first component and plus partial y of the second component, and the fact that I can interchange the order of taking partial differentials, then I can actually see that it's immediately, it's minus. So basically, because it's equal, partial, and that is 0. Okay? So incompressibility, the moment I'm in this form of a stream function, incompressibility, or my equation of continuity, is taken care of. And we went through the figuring out what is vorticity of a flow field like this. And when we plug it into the equation of change of vorticity, with ignoring some terms like this middle term, essentially turns out to be, I didn't prove it, but the middle term turns out to be rather small. This equation of vorticity becomes, so equation, oh, I should learn to use, so this is 2, this is 1. So 2 becomes of C is equal to 0, where this operator nabla to the fourth is basically taking Laplacian twice. Okay. So this is a scalar equation. So that's the benefit. We don't have a vector equation anymore. Note that in terms of this is a scalar equation. And if you recall, W was a vector whose z coordinate was this Laplacian of psi. Just a reminder. All right, so let's remind ourselves of our problem setup. We place the sphere into spherical coordinates. We had a sphere in spherical coordinates. There was no dependence on phi because however I cut the steady state flow around the sphere, it's symmetric in terms of phi, so however I slice it, I see the same thing. Therefore, we don't have phi dependence. So what we had, let me open a new page. So we had flow and the creeping at it, creeping flow around sphere. And my VR was assumed to be VR of r theta. V theta was V theta of r theta, and V phi was 0. And if you recall, so we had a sphere, and basically there's that V infinity, so away from the sphere, okay, I had that V infinity in z direction. So my boundary conditions that was our first exercise, was actually translating those boundary conditions. So the boundary condition that far away from the sphere, that means that r is tending to infinity, my velocity field is v infinity delta z. We had to translate that to the spherical coordinate system, and once we did, we got the first boundary condition that Vr tends to V infinity cosine theta, V theta tends to minus V infinity sine theta, as R tends to infinity. So this was simply translation of the fact that as R tends to infinity, my velocity has to be V infinity delta Z. But delta Z had to be translated to the R theta phi or spherical coordinate system. Do you remember that? We did that last week, right? I did mention that this derivation will take a moment, so there's a good chance you don't remember what we did when I just started it. Our second boundary condition, V theta is equal to 0 at R is equal to R, and our third boundary condition is VR is equal to 0 for inside the sphere and on the boundary. So no flow through the sphere surface or inside the sphere, and no slip on the boundary surface. So my tangential components, both tangential and normal components at the solid surface are 0 because the sphere is static in this flow. Okay. Now we need to actually solve this. We need a spherical coordinate system equivalent for my Nabla-4 operator, my double Laplacian. Okay, and we know that so Laplacian in the spherical in the Cartesian coordinates is just partial square partial x square plus partial y square partial y square plus partial square partial z square of a function. So that's simple to remember. Laplacian in cylindrical and spherical coordinates, of course, has a different form. And you need to go back to your appendix to remind yourself. We're not going to derive, but basically if I do double Laplacian in the spherical coordinates, then we actually have the following. So we need expressed in spherical coordinates becomes what we will refer to e to the 4, just to differentiate the two. And e square is partial r square plus sine theta over r square partial theta. So this is the operator that I have to apply twice. First once and then again on. So you can find this in table 421 in BSL. And by the way, we are working through chapter 4.2 in BSL. 4.1 is skipped for now. It's a time-dependent problem, so it's actually a topic that is separate from this topic. Okay. We also, and I'm just going to give you immediate, so e to the 4 is just I apply, so e to the 4 is of psi is basically I first apply e to the square to psi and then e to the square again, the operator. Also, in terms of, so my velocity components are expressed slightly differently in terms of psi in spherical coordinate system than they are in the Cartesian coordinate system. So in spherical coordinate system, my VR is going to be minus 1 over r squared sine theta, partial psi, partial phi, partial theta, apologies. And v theta is 1 over r sine theta, partial psi, partial r. So this is also something that can be found in this table 421. So now if I apply this, I can see the operator, right? And if I apply this operator twice on my psi, I will see quite a couple operations. I will have partial derivatives in higher order in both r and theta. So our simplifications are not done. We actually have to resort to one of the standard techniques in solving partial differential equation, and that is the first one that you come to think of is separation of variables. So you assume, now why is separation of variables, why would it be justified here? For one, I can see that as my r tends to infinity, I drop the dependence on r, and I can look at the VR and v theta, so it's some function v infinity, which is technically a function of r, and times cosine theta. So I have some separation already when I look at the boundary conditions. Okay? So it's a reasonable assumption. Okay? Because when I plug in r tends to infinity into my function VR and v theta, I should get this boundary condition, right? So boundary conditions dictate quite a bit when solving the problems. So we will also use separation of variables assumption VR or my psi rather, I'm solving for psi. Psi of r theta is some function of r times some function of theta. And I'm going to call them f and g. Secondly, if I could guess one of these functions, that would be really awesome. Okay? Because then I would really simplify my solving the problem. And again, I have to resort to looking at boundary conditions to guess that. So I need a boundary condition such that when I do partial derivative of this function, okay, with respect to psi, so my basically g prime of theta, so my g prime of theta divided by sine theta should come down to cosine theta. That's my theta function up there in VR as r tends to infinity, right? But as r tends to infinity, g of theta stays g of theta, okay, when I take that limit. So I have some traces of what my g of theta should be in my boundary conditions, correct? Okay. So basically my boundary conditions say BCs say that basically, since this is VR and this is VR as r tends to infinity, okay, as r tends to infinity, g of theta sits there pretty, does nothing. Okay? So basically my partial psi partial theta, 1 over sine theta, is equal g prime of theta and should be equal to cosine theta. Maybe there's some multiplication constant in the process, but it's a constant, right? Plus minus a constant, give or take. Also, okay, when I look at v theta, my function of theta is right there. Okay? So basically, 1 over sine theta g of theta is sine theta. What does it look like that g of theta is? Sine squared theta. Okay. Does that work? I can actually figure out. So again, maybe I should actually do this, right? But okay, I can multiply it with some 2 or divide by 2 or whatever. That doesn't change the situation. But the main meat. So if my g of theta is sine squared theta, g prime of theta is 2 sine squared cosine squared, correct? Yeah. So when I divide it by sine squared, I'm going to have something to do with cosine, and there will be a 2 in there. 2 I can always accommodate. Okay? Yes? So whatever is missing here, maybe is missing a multiplier, which is a constant, which I can place into this function f of r, not a problem, to make this work. So I can make this work with g of theta is equal to sine squared theta. So my assumption here will be really c of r theta is equal to f of r sine square theta. So if I can go on and find a solution that fits this, I should be pretty good to go. So if we find the solution for Navier-Stokes in creeping flow regime, so laminar flow very slow, then probably we found the only solution. So Navier-Stokes is not guaranteed to have a unique solution, but in slow laminar flow it is. Yes?
Can you go over that one more time?
Okay. So this part is okay, separation of variables. Fine. Now I'm trying to guess what my g of theta should be. And I can look at my boundary conditions. So when I look at my v theta boundary condition, the number 1, I'm imposing something that as r tends to infinity, okay, my VR, which is this in terms of c, okay, so technically my VR of r theta is equal to minus 1 over r squared sine theta times f of r times g prime of theta, right? If I have c in this form, then VR, I just plug c into this. Okay, so that's by definition. Cool. So basically when I look at the function of c in that, it's 1 over sine theta times g prime of theta. Oh, pardon me. Nobody said anything. There's 1 over sine theta here missing. Okay? So that's my function of c in that portion. Now, as r tends to infinity, okay, that part of the function doesn't change. When I take the limit of my VR of r theta as r tends to infinity, according to separation of variables, the part that is depending on theta doesn't change. It remains a function that it was. Okay? And that function should go to g, should be actually cosine theta then, because it remains intact. Right? So 1 over sine theta times g prime of theta should be cosine theta. Okay? So g prime of theta should be, and I say not necessarily equal because I could have it multiplied by 7 and nothing would change, right? So I'm not going to say precisely equal, but it should scale as sine theta cosine theta. Okay? Now from the second one, b theta, I have 1 over r sine theta, partial c partial r, is essentially 1 over r sine theta times f prime of r times g of theta. So theta portion of it is 1 over sine theta g of theta. Okay? And that should be sine theta, give or take. Maybe times 7, maybe times minus 1 over r, whatever. So whatever is rest is a function of r or some constant. Okay? So when I actually look at that, g of theta, it gives me a clue that it should be sine square theta. And when I plug it into this one, it complies, because if I do derivative of sine square theta, it's 2 sine theta cosine theta, so it's very much on par with my first mandate. Okay? So I can actually then guess what my function of theta is and be busy finding function of r. So let's get busy finding function of r. Okay. Okay. So all that is left to do is plug psi of r theta, which is some function of r sine square theta, into my e square of e square psi is equal to 0. Okay? So we said e square, so basically what I'm looking for is first this part. So I already said the operator is partial square partial r square plus sine theta over r square partial partial theta of 1 over sine theta partial partial theta, all applied to psi. And that psi is f of r sine square of theta. So this is the function that I'm applying this operator to. So partial square partial r square of this function here is simply f double prime of r times sine square theta, right? Oops, what did I do here? So I have f double prime of r sine square theta. So that is applying this term on this. I get this. And then, oh boy, so I'm gonna do this layer by layer. So it's plus sine theta over r squared partial partial theta of, and then what I have here is 1 over sine theta. Partial partial theta of this function is essentially f of r 2 sine theta cosine theta. So this applied to that is this part. All right, so these two This can go. Okay. So now I have equals 2. I leave the first one as is. And it's the second one that is a little hairy. So I can put f of r outside of this taking partial derivative with respect to theta because they don't. And I can take actually 2 outside as well. So what I have is partial cosine theta, partial theta, which is minus sine theta, right? So finally, what I have here, I have sine square in both of these terms. Times, and I have f double prime of r minus 2f of r over r squared. So it appears, now I look at this as a formal operator, okay? It appears that when I have psi in the form above, e squared to the psi pretty much does nothing to sine squared. That remains the same. And it operates only on function of r as this. So I can formally actually think of, if psi of r theta is f of r sine square theta, then e square is simply a second order derivative minus 2 over r square applied to function f. And then just sine square theta. Does this make sense? So it appears that I'm operating only on f. And formally I can write this way. Why am I doing this? Because I can simplify my, now I have to apply it twice, right? So if I do e square is e square of e square psi, right? It seems that sine square theta, nothing will happen to it, and I'm just going to work on f. Yes?
At the operator there, we don't have f, right?
We don't have f yet. We are looking for f. We guessed g. I mean, we have to search for something. We can't guess everything. Okay, works only on f and leaves sine square theta alone, which it does because we found the correct function of theta, right? It's not an accident. We actually identified the correct dependence on theta, and that's why this happens. All right. So, okay. This is now basically ordinary differential equation, but it's still fourth order, right? Because I gotta do this twice, right? And it depends only on r. So what is going to be my second guess on the form of f? So it's not a sine or cosine because we don't have an angle here. What is the simplest function of r you can think of? R to the square. What is r to the square? A polynomial. So a power of r. So let's look for all powers of r that will actually disappear if I apply this operator twice. Does that make sense? So basically we will look for, and then if we found them, good, we found a solution, right? So let's look for powers of r or polynomials that comply with e to the 4 is equal applied to f of c rather is 0. So then I'm assuming f of r is some constant times, I'm just gonna, of course I could have some constant multiplying it, so I'm just gonna look at this power, but we will assume that we have a constant. Or so technically f of r is a constant times r to the n, but okay. Then my f prime of r is n r to n minus 1. Okay. F double prime of r is n minus 1 n r to the n minus 2. Okay. So when I actually apply this operator twice, I'm going to go, is everybody done? I need to go to the next page. I'm working on finding a software that is scrolling through as you go, but it's not as effective than to break things into pages that I can put as notes. So that's a dance. So if you see something, let me know. I'm pretty sure within 6 months it's going to be available. Yeah. So basically when I have, what I'm looking at is d square dr square minus 2 over r square applied on, what was that? I'm going to remind myself, it was f double prime of r minus 2 over r f of r. So my e to the 4c is equal to this, and then times sine squared theta. So when I plug in, so this is that operator applied twice, okay? So I need to do it once, but let me actually write what this is first. So it's d squared dr squared applied to what f double prime is n minus 1 n r to the n minus 2 minus 2 r n minus 2. That's r to the n divided by r squared, right? Sine theta squared. Okay. Now I keep going. I have to actually take the second derivative. So this I can simplify it first. Of what? So it's actually n squared minus n minus 2 times r to the n minus 2. I divided by r squared, right? So there was f of r, 2 times f of r divided by r squared. F of r is r to the n. So divided by r squared, it's r to the n minus 2.
And then the f has to have r squared.
Oh, was it r or r squared? It was r squared, sorry. So my bad. Sorry. I'm just checking if you're paying attention. And you are. Good job. Okay, so then I just apply those derivatives or that operator again. This is just a constant, whatever it is. So it's n squared minus n minus 2. Okay. And then times, so second, n minus 2 times n minus 3 r to the n minus 4. So that's the second order derivative of r to the n minus 2, and then minus 2 r to the n minus 4. I'm going to squeeze in that sine squared theta. I don't need it anyway, but I'm dragging it along. So what do we have? We actually have n squared minus n minus 2 times n squared minus 5n plus 6 minus 2 plus 4 r to the n minus 4 sine squared theta. So that is my e to the 4 applied to c. Are we agreeing with this algebra so far? It's boring, but it's straightforward. So this has to be equal to 0. And as an operator, if e to the 4 of c of r theta as a function is going to be equal to 0, it has to be equal to 0 for all r and all theta, right? For all r and theta. So this is a non-zero part, right? Then obviously this has to be 0. So I gotta find zeros, or I gotta find n's for this, which has to be. So this part has to be 0. So I have to find n for which that is true. So my first option is that n squared minus n minus 2 is equal to 0. This is really n minus 2 times n plus 1. Or you just solve the quadratic equation, however you want to deal with it. So my n is either minus 1 or 2. So basically 1 over r or r squared are my power functions that work here. It's not necessarily a polynomial, it could have 1 over r in there too. And my option 2 is that n squared minus 5n plus 4 is equals to 0. And this is really n minus 1 times n minus 4 is equal to 0. So my n is either 1 or 4. So the functions that work are 1 over r, r squared, and r to the 4. Or at least those are the functions that satisfy this differential operator being equal to 0. So now our general f, so in general, since all of these work, I'm going to superimpose. So I'm going to assume that f of r is equal to c1 r to the minus 1 plus c2 r plus c3 r to the square plus c4 r to the 4.
Why don't you just do 1?
Huh?
Why don't you just do 1?
Because then I might be not looking at the complete solution. Obviously, all of them work, so I should assume that it's a superposition. And I have 4 boundary conditions to work with, so I should have 4 coefficients to work with, or else I might not satisfy my boundary conditions. Okie dokie, and then all we need to do is look at the boundary conditions. So basically C1, C2, C3, C4 are found from BCs. So my first boundary condition is on VR and V theta as r tends to infinity. But I have to find what VR and V theta are in terms of this f, right? Everybody done? Okay, so my first boundary conditions are in terms of VR. So when I actually apply VR of r theta is minus 1 over sine theta applied to f of r g or my sine squared theta, right? And that is minus 2f of r cosine theta divided by r squared. So this has to tend to v infinity cosine theta as r tends to infinity. So when I plug in my f of r over r, so f of r over r squared is what? It was c1 over r cubed plus c2 over r plus c3 plus c4 r squared.
So that first term is less than the first one, right?
This here, deep C, yes. I did it though. As I was doing it in my head, I did dd theta and I didn't write it down. I can't work. My brain is not the parallel machine. It's a serial one. That's a problem, but oh well. So minus 2 times this is minus 2 times this. And that has to go to v infinity as r goes to infinity, right? So basically my C4 should be 0, otherwise it's gonna blow up. So first thing, C4 has to be 0, or else I'm in trouble. And as r tends to infinity, these first two terms will zero out. So basically the second part of it is minus 2c3 should be equal to infinity. So c3 is minus 1/2 okay. So then second part is that VR of r theta, both v theta and VR should vanish on the surface r is equal to r. So VR of theta should be equal to 0 at r is equal to r. So what is my VR? It is, and cosine theta part can't vanish, so I'm gonna go again. So it's minus 2c1 over r cubed plus c2 over r plus c3 cosine theta has to be equal for r and for r. Okay. So basically c1 over r cubed plus c2 over r plus c3 should be equal to 0. And I know what c3 already is, so this is basically an equation in c1 and c2. And I need one more equation for c1 and c2, and I'm going to get it with v theta at r is equal to r. So this is my first boundary condition, second boundary condition, and third. So v theta is 1 over r sine theta partial r of f of r sine squared theta. So you gotta take a derivative of my f of r. So it's 1 over r sine theta times minus c1 over r squared plus c2 plus 2c3 And the C4 is 0 anyway, R. So then I'm gonna ignore the theta part because I cannot zero it out. So what has to be 0 is minus C1 over uppercase R cube plus C2 over R plus 2C3. So I know C3 already and C4. Okay. So you can plug it in. I'm just going to go dot, dot, dot. C1 is minus R cube V infinity over 4. And C2 is 3/4 R V infinity. So when I plug it into, this is actually my form of V theta and VR that I already plugged in. We will get the final solution. Whoops, I went way over time. Sorry about that. We're gonna just plug it all in and look at it next time.